In this module, we're talking about carbon-carbon bond formation via substitution at the alpha carbon. Again, the alpha carbon is a carbon next to a carbonyl group. So if that alpha carbon has hydrogens, those hydrogens are more acidic than a normal sp3 hybridized CH bond. So we're going to look at that acidity trend and then look at the generation of enolates under basic conditions and enols under acidic conditions. So first, let's recall the acidity trend based on hybridization. So CH bonds follow this trend. sp3 hybridized carbon H bonds are less than sp2 are less than sp. So what does that look like visually? So if we're just looking at say methane, which has sp3 hybridized carbon, and the pKa of that CH bond is approximately 50. Now if we change hybridization, and now we're looking at, let's say, ethylene, again, these carbons are sp2 hybridized. pKa value here, about 45. And then finally, if we're looking at acetylene, with sp hybridized carbon, the pKa value drops considerably to 25. And again, we rationalize that based on the percent S character. So as we look through that trend, the percent S character increases. Here we have 25%, 33%, and 50%. And the reason that's important is because the S orbital is viewed as a sphere that is closest to the nucleus. So once that CH bond is broken, the negative charge on the carbon is closer to the nucleus. So if we're examining an alpha carbon in the most general scenario as follows. We have our carbonyl group. The carbon next door is the alpha carbon. This alpha carbon is sp3 hybridized, and therefore you would expect the pKa value of those CH bonds to be approximately 50. However, that is not the case. The actual pKa values are 20 to 25, depending on what R and R prime are. So how do we rationalize this observation? So if we consider the following, if we treat this compound with some base, and again, the verb of a base is to abstract a proton. I'm going to say this base is negative. It's abstracting that proton. We're breaking the CH bond. The lone pair of electrons then resides on the alpha carbon. So in the process, we're losing the conjugate acid of that base. The lone pair of electrons on the alpha carbon can then, through resonance, be delocalized onto the carbonyl group. As a reminder, this is the resonance arrow. And this resonance hybrid here is called the enolate. And that word is derived from alkene, alcohol, and remember that ATE ending indicates negative charge. So we have an enolate. Again, an enolate is going to be a nucleophile. So that supplies the electrons to form a bond. The nucleophile reacts at the alpha carbon. Alternatively, if we are under acidic conditions, we will form an enol, and that is neutral. So let's use this general acid here, HA. We've seen plenty of times that a carbonyl group, when treated with acid, will be protonated. We now have a protonated carbonyl. We can draw a resonance form for this. Where the positive charge is now on the carbon. And then we're going to use the conjugate base of our original acid. To abstract a proton from the alpha carbon. And essentially what this is doing is an elimination. We then lose that acid, and at this point we form the neutral species. Compare that to above. This is called an enol. So under basic conditions, we form enolate. Under acidic conditions, we form the enol. So in this screencast, we've looked at the acidity trend based on carbon hybridization. We've then looked at the alpha carbon under both basic and acidic conditions to form enolates and enols. And these are the nucleophiles that we will learn in subsequent reactions to react with electrophiles to carry out substitution of the CH bond at the alpha position.